Hi everyone, welcome to next lecture of Chemical Engineering Thermodynamics. I hope you remember the last class where we discussed and we started chemical engineering second law of thermodynamics. Clear? So second law of thermodynamics आपको याद होगा, right? We have discussed the Kelvin-Planck statement. ठीक है, तो उस टाइम पे मैंने बोला था, right? So what is the requirement of the second law of thermodynamics? ठीक है, तो उसके बाद हमने बोला था कि हीट इंजन कैसे वर्क कर रहा है, राइट, एंड रेफ्रिजरेटर एंड हीट पंप वो सब हमने डिस्कस किया है. तो उस टाइम पे मैंने बोला था व्हाट इज द यूज ऑफ दिस रिक्वायरमेंट ऑफ द सेकंड लॉ ऑफ थर्मोडायनामिक्स, राइट. तो उसका मेजर यूज मैंने ये बोला था, इट इज रिक्वायर्ड टू फाइंड द मैक्सिमम थियोरेटिकल लिमिट, राइट, मैक्सिमम थियोरेटिकल लिमिट फॉर द साइक्लिक डिवाइसेस, राइट. सो जो हमारा साइक्लिक डिवाइसेस है, लाइक फॉर एग्जांपल हीट इंजन या रेफ्रिजरेटर या हीट पंप, राइट, ऐसे जो साइक्लिक डिवाइसेस है उसका जो मैक्सिमम थियोरेटिकल लिमिट हम सेकंड लॉ यूज करके कैलकुलेट कर सकते हैं. क्लियर? सो दैट इज वन ऑफ द मेजर यूज. ठीक है, आई होप द बोर्ड इज विजिबल, राइट. सो यस, clear? So that is okay. Now for maximum theoretical limit, what is the meaning of this maximum theoretical limit, right? So how can we maximize this work, right, or maximum efficiency? How can we increase the maximum efficiency, right? So that is a question. So हम यहाँ पे देख सकते हैं what is the meaning, right? मतलब मैंने already heat engine discuss किया है. You can see here heat engine. So how is the working of a heat engine? That is, we have a high temperature source, right? So from the high temperature source we are taking heat and we are converting this into a work output, and we are rejecting this back to a low temperature source, sorry, sink. Clear? तो मैंने बोला था this, if for example QH अगर 1000 joule है, maximum we can get is what? Below 1000 joule. That is, for example, sometimes the maximum we can get the work output is 750 joule. The remaining 250 joule we have to send it back to the surrounding. Clear? Now the meaning is what? What is the efficiency here? What is the heat engine efficiency here? 75%, 750 by 1000. ठीक है. So what is the meaning? The maximum efficiency, right? How can we maximize this efficiency? That's what we are going to study, right? आपको मैंने वो gate exam वाला example भी दिया था. मतलब maximum marks we can get is what? 100, but 100 is impossible. So we will see up to maximum level, like 90, 85, up to maximum level. How can we reach that? Right? So we are interested to study how we will be able to get that maximum theoretical limit, and what will be that maximum theoretical limit. Right? We have to know what is the maximum work we can score at least. Right? 100 is not possible, okay, but 90 possible है क्या? वो हमें पढ़ना चाहिए. Right? That we need to understand. For that we are using what? Our second law of thermodynamics. Clear? So this is the meaning. Right? So how it is possible? That's what we are going to discuss. Clear? यहाँ तक तो okay ना? Now, right now, when these cyclic devices, right, that is the work consuming or work delivering, right, so work consuming or work delivering these cyclic devices, right. For example, when these cyclic devices work in the reversible processes, right, work irreversibly, we can get what? Maximum efficiency. That is what theoretically they say, according to your Carnot cycle, or according to whoever scientists who have developed this, right, according to second law, what they are actually saying is, if we do these processes reversibly, you will get the maximum output, right, or you will get the maximum result, right. So that is obvious, right, right, in life everything, right, if you do everything ideally, you will get the maximum thing, right. So that is the same thing. So how we are going to understand that? That is our question, right. So in cyclic devices, what happens actually? Right, if you remember the cyclic devices, one part of the cyclic device we have work done on the fluid, and in the other part of the cyclic device we have what? Work done by the fluid, right. So take the example of the refrigerator now, right. Refrigerator के एक side पे क्या हो रहा है? Compression, right. One side of the refrigerator we are having compression, that is work done on the system or on the working fluid. Right, in the second side we are having a throttling valve, or we have an expansion valve. So this side we are having what? Expansion. Expansion is what? By the system or by the working fluid. Clear? So यहाँ पे आप देख सकते हैं, right, so दोनों साइड पे, right, आपके जो सिस्टम है और आपके जो साइक्लिक डिवाइस है, one side of the cyclic device we are having what? Compression, and other side we are having expansion. Clear? So we have both compression and expansion. The meaning is very simple. We have both work done on the system and we have work done by the system. Clear? Now how can we make the cycle efficiency maximum? That is how we are able to find this maximum cyclic efficiency. That is the question. Right? How we are able to extract this maximum cyclic efficiency, that is the only problem we have. Clear? Now for getting compression done, right? For getting compression done, हमने already पढ़ा है, right? That is, when we do compression, we need to give some energy, right? We need to give some work input, right? Now if you do this compression reversibly, if it is a reversible compression, right? We need what? Right? We need only least amount of work. Understood this? Right? That is, if you compress this reversibly, you require only minimum effort. Right? But if you do it in irreversible manner, you may require what? More work. Clear? So this is the point. Now same way, come back to expansion. Expansion is the work done by the system. Clear? So when we do expansion also by reversible processes, right? When we do expansion also by reversible processes, expansion is work done by the system. You will get what? Maximum amount of work from the system. Is that fine? So when we combine these two, right? When we combine these two processes, that is your expansion and compression both, what will you be able to achieve? You will be able to achieve what? Maximum cyclic efficiency. राइट इसके लिए मैंने एक एग्जांपल बोला था, आपको याद होगा, राइट? फर्स्ट क्लास में मैंने बोला था, राइट? व्हाट इज द इंपॉर्टेंस ऑफ ए रिवर्सिबल प्रोसेस, आपको याद होगा ना? मतलब फॉर एग्जांपल माइलेज, कार माइलेज का एग्जांपल फॉर एग्जांपल, राइट? सो कंपनी आपको क्या बोलता है माइलेज? दे आर गिविंग यू ए माइलेज ऑफ 25 किलोमीटर पर लीटर, राइट? एंड व्हाट इज देयर statement? They will say, sir, our company mileage is 25 किलोमीटर पर लीटर, लेकिन ये माइलेज आपको मिलता है क्या? नहीं, right? You will never get the promised mileage. It is 25 kilometer per liter. This was based on what? Ideal case. This was based on what? Reversible case, right? Matlab they have tested everything, that is from a straight road, right? Very good engine conditions or whatever, top gear, whatever thing. Ideal mileage is 25, लेकिन आपको कितना मिलता है? Right? Because we drive that way and we don't have any ideal road and fuel condition, and we will be getting what? 12.5 kilometer per liter, for example. So what is the efficiency? 50. Right? So according to this, when the work is done by the system, you will get the maximum amount of work when we do it reversibly. Same example I have applied here also, right? When we are deciding to study something, right? When we are planning something, हमारा प्लान के हिसाब से क्या होता है? 1 hour पे आपका पूरा टॉपिक खत्म. 1 hour, we only morning during exam day we will plan like this, right? Morning 6 o'clock I will get up and 6 to 7 the chapter is over. बट ऐसा होता है क्या कभी लाइफ में? नो, वी विल टेक मिनिमम 4 hours टू कंप्लीट द प्लान सब्जेक्ट, राइट? तो आइडियली किया तो लीस्ट अमाउंट पे हो जाएगा काम, राइट? आइडियली किया तो 1 hour पे हो जाएगा काम, लेकिन एक्चुअली क्या होता है? 4 hours. सो व्हाट इज योर एफिशिएंसी? 25%. Clear? So compression is the work done on the system. When it is work done on the system, with minimum effort it will be done. Right? So within 1 hour the problem is solved, but actually you require what? More, right? So अगर आपका compression reversible नहीं है, right? So if it is not a reversible compression, what will be happening? You may require more work, right? And if it is not a reversible expansion, you may be getting very less amount of work from the system. But when we combine the reversible process here and here, what you will be getting? You will get the maximum cycle efficiency. Because one side you are compressing reversibly, you require only this much amount of work, and one side you are getting this much amount of work from the reversible expansion. So combining this, you will get the net work done. And my question is, can the net work done be zero? Zero हो सकता है क्या net work done? अगर हमारा cyclic engine और cyclic refrigerator, right? So refrigerator का work done zero है, net work, then the refrigerator is not working. ठीक है? So your net work done cannot be zero, right? It should be more than zero. That's why we are saying, that's when we are saying the refrigerator is working, the AC is working. If the net work done is zero, means it is not working. Clear? Simple. So if we want to maximize the cyclic efficiency, we need to combine the reversible processes. Clear? I hope you understood that. Clear? So if you want, you can write the statement. Right? If you want, you can write the statement. The cyclic efficiency can be maximized. Right? The cyclic efficiency can be maximized. The cyclic efficiency can be maximized by using processes that requires least amount of work. By using processes that requires least amount of work and processes that deliver, right, and by using processes that deliver maximum amount of work, that is by using reversible processes, right, by using reversible processes. Clear? Now, right, now what is the importance of using reversible processes in a cycle? Right, what is the use of a reversible cycle then? Right, if we use all the process reversible, then we can call it as what? It is your reversible cycle, right? The entire cycle, all the processes are reversible. Now, what is the use of this? Because this thing can be considered as a model, right? This reversible cycle can be considered as a model so that our actual cycles can be compared with this model. राइट क्योंकि आपके पास जो माइलेज 25 दिया है दैट इज द रीजन वी आर कंपेयरिंग आवर माइलेज ना राइट क्योंकि कंपनी ने आपको बोला है 25 इज योर माइलेज राइट यू हैव दैट थिंग इन योर माइंड ना मतलब कंपनी इज सेइंग 25 किलोमीटर पर लीटर बट आई एम नॉट गेटिंग 25 बिकॉज यू आर कंपेयरिंग योर एक्चुअल माइलेज विद द रिवर्सिबल माइलेज. See, same way, whatever value you are getting from the reversible cycle will be acting as a model so that we can compare with what? Your actual cycle. Right? Your actual processes can be compared, or your actual heat engine or actual refrigerator, everything can be compared with the reversible cases. Right? So we can say, okay, this particular thing is this much efficient. Right? But still we have methods to improve. Right, so the same thing. आपको याद होगा after every GATE exam, every institute, right? So we'll be conducting this interview of the toppers, right? GATE rank AIR 1, AIR 2, right? Like you can see it on the GATE Academy channel also. We have done a lot of interviews with the toppers, right? So who are these toppers? They are the reversible cycles, right? They didn't get 100 out of 100, right? They didn't get 100 out of 100. Is it? No. They didn't get 100, but what they got is maybe 90. So 90 marks is the ideal case in that, right? It is the reversible cycle. Now whatever we are getting, we are going to compare it with them, right? So our aim will be to get to this 90, so we will be comparing ourselves with the 90, that reversible model, same thing, right? So our actual cycles will be compared with the reversible cycle. Clear? So the example of a reversible cycle is what? Right, your example, the major example for a reversible process is your Carnot cycle. This is your major example of a reversible process. So this Carnot cycle is always a reversible cycle. So what is the use of this Carnot cycle? The use of this Carnot cycle is we will be able to find the maximum theoretical limit. So every refrigerator, every heat engine, every heat pump can be compared with what? A Carnot refrigerator or Carnot heat pump or a Carnot heat engine, because it is a reversible cycle. Clear? So this is the meaning of Carnot heat engine. So generally Carnot cycle के ऊपर आप लोगों ने, like if you are a third year or final year student, right? So if you are a passed out also, right? When you were in third year, when you were studying this thermodynamics, you might have written essays on it. है ना मतलब this is a 10-15 mark question in every syllabus, every case in thermodynamics. Carnot cycle explained, right? So you might have written a lot of things about Carnot cycle, but sometimes, but to be frank, when I was in my final year when I was in third year, I also written the essays, but I don't remember it, right? And when in the interview, if they are asking Carnot cycle, you will be saying what was this, right? So simple thing, whenever you have to understand it is a reversible cycle, yeah, right? It's a reversible cycle and it is for comparison, right, with the actual cycle. So this gives us the maximum theoretical limit. This is your topper, right? This is your topper to which you are comparing yourself. Okay, this is the AIR 1. Carnot cycle is your AIR 1, right? All India rank 1, and always the people will be comparing with him, right? Okay, this is the highest value we can get. Okay, the AIR1 will not have 100 out of 100, but he may be getting what? 90, for example, sometimes 85. So 90 is the maximum value we can score, right? So 90 is the maximum value possible in that exam, because that's why he's number one, right? Now there are other students who got 75, so he may not be ideal, right? He may be a irreversible process, right? But if you compare the student who got 60 and 75, who will be more irreversible? He will be more irreversible, right, compared to him, because he is close to the reversible. Now if we compare 75 and 80, who will be more irreversible? More irreversible is 70. More irreversible, I am saying, because 80 is close to the reversible case. Simple. So if we see the person who scored 30, he is very much irreversible, right? So that's the meaning I am saying, right? So that is the meaning I am saying. I hope you understood what is reversible cycle, what is a reversible cycle. But for gate, what we need in Carnot cycle is, what are the processes in Carnot cycle, why it is used for the calculation, etc. That's what we require, right? We don't need to write any essays here. Clear? I hope you understood this as well, right? Now we are having 4 processes in a Carnot cycle. That 4 processes you need to remember. So the first process is 1, 2, 3, 4. You have 4 processes, right? So obviously I'm writing it. All the processes should be what? Reversible, because it is a reversible cycle. So this is also reversible. Second process should also be reversible. Third is also reversible. Fourth is also reversible. Every process should be reversible. Clear? Now second one. So my first process is reversible isothermal expansion. Clear? Now if it is a cycle and if you have 2 expansion processes, to complete the cycle you need what? You need 2 compression, right? Because if you expand 2 times, you have to compress 2 times, right? Then only you will get back to the initial state, because it is a cycle. Okay? Because it is a cycle, so you have to get back to the initial state. Now reversible isothermal expansion, second will be reversible adiabatic expansion, right? So same way we have reversible isothermal compression and you have reversible adiabatic compression. Clear? So these 4 processes, right, in a combination will form what? Will form your Carnot cycle. Done. Now, even though we don't require further in Carnot cycle, right, that is, the explanation is not required, we will see how we are able to achieve a reversible process, right? That is important, even though not for gate, for your understanding, right? So how we are going to explain it, wo aapko samajhna chahiye, right? How we are able to achieve these 4 processes in a Carnot cycle. Even though reversible process is not possible, right? How we are able to approximate this. Clear? So we'll see, right? So aap ek kaam kar lo, like we can consider a system, okay? Consider a system. It is a closed system, okay? And I am saying there is a piston cylinder arrangement. So this is my piston cylinder arrangement, okay? So this is my piston and this is my state 1. Clear? So we have a gas at a temperature TH. Clear? So this is my state 1. So now I am doing my first process from state 1 to state 2. What is that process? Expansion. So when I expand this, what will happen? The piston will move from the first position to, right, piston will move from the first position to second position. This is my second position. Clear? So initially we have a gas inside the piston cylinder arrangement which is at a temperature TH. Now we are expanding. Now tell me, when we expand, what will happen to the temperature? When we expand a gas, what will happen to the temperature? When we do expansion, decrease, right? Temperature will go down. Now we are doing the first expansion reversibly. So what we are saying is we are going to do as a slow expansion. What is the meaning of slow expansion? Slow expansion meaning is we want the driving force as slow as possible, as small as possible, so that it is a reversible process. and obviously we can say what it is a frictionless piston. So the process is reversible, or we can say it is close to reversible. Clear? So it is a very slow expansion. Now when it is very slow expansion, what will happen? The temperature also will decrease very slowly, right? But it should be a reversible isothermal expansion. That is, we don't want the temperature to change. So what we will do is, right, we will keep a temperature source here, which is at a temperature TH, high temperature source, okay, TH. Now when you have a small change in temperature, that is when we expand very slowly, when a small expansion happens, your temperature here will become what? TH minus DT. Small temperature is reduced. Now what will happen is, you will have a heat transfer from the source to inside. For the DT temperature difference, you have a heat transfer. So what will happen? Temperature will remain constant at TH. Clear? Again some more expansion. Again temperature will reduce by an amount of DT. Small value of heat is transferred. Now we reached from temperature TH. After expansion, your temperature is still TH, because it is an isothermal expansion. So the heat transferred during the process is QH. No problem, right? Why there is a heat transfer? Because it is an isothermal expansion, right? To keep the temperature constant, we need to supply heat. Simple. Now what is second process? Reversible adiabatic expansion. That is, you can see here, this was your system, right? Where is your piston? Your piston is here, right? Here is your piston. Now from state 2, we are expanding the system again. Now the piston is here. Now this is your state 3. Right, we are having another expansion, but this time, right, this time what happens? Here the temperature is TH, but this time what happens? It is an adiabatic expansion. That is, we are insulating the cylinder, or the piston cylinder arrangement we are insulating, so that we cannot have the heat transfer. If there is no heat transfer during expansion, what will happen? Temperature will decrease. So your temperature will change from what? Your TH to TL. Temperature is changed from TH to TL. Is that a problem? No, because it is a reversible adiabatic expansion. Now since we have expanded 2 times, to complete the cycle you need to compress it 2 times. Simple, right? If you remember that refrigeration cyclic device, one side you have compression, one side you have expansion. Same way, right? So what will be the third step? Right, third step will be, I will be saying like this, right? Our system was here. This was the third state. From the third state, we are compressing the system back to fourth state. Now, what kind of compression we are doing? We are doing an isothermal compression, right? We are doing an isothermal compression. So when we increase, right, when we compress something, what obviously will happen, right? Your temperature here, right, your temperature here was what? TL, right? TL was your temperature here, but when we compress, you have a increase in temperature, TL plus DT, right? Here at the third state, your temperature was TL, but when you compress, what will happen? Your temperature will increase by an amount DT, right? So when you have an increase in temperature, we are not allowed to increase the temperature because it is an isothermal compression. So we will bring another source or another sink, we can say, at a temperature TL. Now when you have an increase in DT, heat will transfer in the opposite direction. So it is a slow compression. During the total compression, you are having a heat transfer of QL, so that your temperature is maintained at the same temperature TL. Same thing. Now what will be the last process? Last process will be from the state 4, right? This was your state 4. Since it is a cycle, right? Since it is a cycle, you have to bring it back to the initial state. What is the initial state? State 1. For that, you have an adiabatic compression. So, आपके जो भी cylinder is again insulated. Now, when it is an adiabatic compression, your temperature TL will be increased to TH. Now, you can see initial state and final states are same. TH, TH. Right, now it is a cycle. right? So this is a reversible expansion, reversible compression, 4 processes are there. So this combines our Carnot cycle, right? So this is the way we will be achieving our Carnot cycle. Even though these things are not important for your gig, but you should remember these 4 processes. Then now we will understand how we are going to represent this Carnot cycle in our PV diagram, right? How we are going to represent. Clear? So write all these processes, right? 4 processes, then we will go for the PV diagram. Clear? I hope you are able to see this diagram, right? Now I will explain how we are drawing the diagram, okay? So this is the PV diagram, okay? This is the PV diagram, pressure volume diagram. Now you have 2 compression and 2 expansion, right? So this is your TH, that is high temperature line, right? And TL, this line represents your isothermal curves, right? TL, TH. Now the process 1 to 2 represent what? Process 1 to represent your reversible isothermal expansion, right? If you remember the PV diagram of an expansion curve, if you remember PV diagram of a isothermal, it will be like this, right? PV diagram of an isothermal, right? That is at constant temperature, your diagrams will go like this. Clear? So we have drawn 2 isothermal curves, right? That is at a different 2 temperatures, right? 1 to 2 is okay. And if you remember, the slope of adiabatic curve is more than the isothermal curve. That's why, right? If you remember, slope of adiabatic is gamma times the isothermal, that you remember. So that this 2 to 3, we have an extra slope. So 2 to 3 represent what? 2 to 3 will represent your reversible adiabatic expansion. Now remember, if it is an expansion, whenever you draw this, remember these things. Expansion means your pressure should decrease, volume should increase. Here pressure is decreasing, volume is increasing. You have to draw it accordingly, right? Otherwise it will be not correct. Same way, you can see from 3 to 4, it is an reversible isothermal compression. So when it is compression, you can see the pressure is increasing, volume is decreasing. Now 4 to 1 is again adiabatic. That's why you are having slope greater than your isothermal curve. So now complete the diagram, right? So complete the diagram. So this will represent your Carnot cycle, right? So this particular diagram will represent your Carnot cycle. Clear? So 1, 2, 3, 4, that this particular thing will represent your Carnot cycle. Now how will you find, right? How will you find the work done by the Carnot cycle? Obviously the area under the PV diagram will give you the work done. Clear? Area under the PV diagram. So what we will do is very simple. What is the area under the expansion? Expansion is 1, 2, 3. This complete area will give you the expansion work. Right? What will be the compression work? Compression work will be 3, 4, 1. Right? So when you do that, you will be getting what? You will be getting the area under the cycle. Right? Area inside this particular thing will be your work. Now if you remember, during expansion, right? During expansion, you were having a heat transfer QH into this particular system. Right, during that compression, isothermal compression, you have a heat transfer out, and the inside whatever you have is your work output. So we will be saying what your work output for a Carnot heat engine is equal to QH minus QL. These things you can understand. Clear? So the area under the Carnot cycle, right? So will give you the work done, net work done by a cyclic device. Clear? So that also you can do. So work output is what? QH minus QL. So complete the Carnot cycle. 1, 2, the process 1, 2 is what? It is your reversible isothermal expansion. 2 to 3 is your reversible reversible adiabatic expansion. 3 to 4 is obviously your reversible isothermal compression, and 4 to 1 is reversible adiabatic compression. Clear? So these are the 4 things. Right, so complete the diagram and mark all the things. Done. Now, right, now being the reversible cycle, right, because it is a reversible cycle, right, Carnot cycle is a reversible cycle, remember, right? So whatever we discussed, Carnot cycle is a reversible cycle. So Carnot cycle being a reversible cycle, this Carnot cycle will be the most efficient cycle, or Carnot cycle will be having the maximum efficiency when it is working in between TL and TH. for these two temperatures, right, for these two lower limit and upper limit, this Carnot cycle will be your most efficient cycle. Clear? No other cycle can cross the efficiency of Carnot cycle because it is the reversible cycle. Clear? Now, so this is your Carnot cycle for a heat engine, or we can say this is a Carnot heat engine. Now, when you want to draw about, right, when you want to draw Carnot refrigerator, right, when you want to draw Carnot refrigerator, right, when you want to draw Carnot refrigerator, we will draw what? We will do a reversible Carnot cycle, simple, right? In what is the difference between a heat engine and your refrigerator? Instead of this work output, you will have what? You will have a work input. Same thing, right? Instead of a work, if you remember this, what was your refrigerator block diagram? We will be taking QL from your freezer compartment, right? And we will be rejecting QH to the surroundings by the use of a work input. So instead of work output, in your Carnot refrigerator or reversible Carnot cycle, right, reverse Carnot cycle, right, so in your Carnot refrigerator you have this opposite, that is, we will be taking QL from freezer compartment and we will be rejecting this to the outside, right, we will be rejecting to the outside. So to denote that, we can make this opposite in direction. To denote it as a reverse Carnot cycle, 1, 2, 3 and 4. Right, to understand it is a reversible Carnot cycle, the only difference is what? What is the major difference? We are taking QL and we are rejecting QH. Taking QL, rejecting QH. Right, so this will be a reversed Carnot cycle. Right, this is your reverse Carnot cycle. So reverse Carnot cycle example is what? Carnot refrigeration cycle. Right, so when you draw the Carnot cycle for refrigeration, you will be having this diagram. Right, only what is the difference? QL, QH out, using work input, not in output. Clear? So that is also understood. Clear? I hope it is done. Clear? Now you are having, what you need to understand is, for solving the problems, right, for solving the questions based on Carnot, what you have is Carnot principle, right? So the Carnot ने मतलब खाली ये system develop नहीं किया है, खाली ये cycle नहीं बताया, right? He has given up some principle, right? So the first principle is, I will say the principle, right? I will give you the principle. That first principle is, if you have two things, that is, if you have two temperatures, right? So that is, we have a source and if you have a sink. Obviously, the first statement I have already told, that is, a reversible cycle will have the highest efficiency. Right, reversible cycle will have the highest efficiency compared to all the irreversible cases. Clear? To understand that, I will draw three diagrams. Okay, three diagrams. That is, I will draw three heat engine. That is, this is your heat engine 1. This is your heat engine 2, and this is your heat engine 3. In all cases, your TL and your TH is same. For all these cases, your TH and TL is same. All the three heat engines, in all cases, your source and sink is having the same temperature. Source and sink is having the same temperature. Okay. So then only we can compare, right? We are trying to compare it with three cases. So this is the work output, this is the work output, and here this is the work output. Clear? So see the three examples of three heat engine. Clear? So what is the first Carnot principle, right? The first Carnot principle is very simple. The efficiency of an irreversible Carnot cycle, right? So I am saying, for example, this is an irreversible Carnot cycle. It is an irreversible heat engine. So efficiency of an irreversible heat engine will be always less than the efficiency of reversible, right? So if I say this this engine is also reversible heat engine, this is also reversible heat engine, then according to Carnot principle, what he is saying is both these reversible heat engine will have a higher efficiency compared to irreversible. Simple. Same enough, right? Irreversible heat engine will have a low efficiency compared to the reversible. Now, come back to this. We have one more principle, right? If you are having source temperature and sink temperature same for both reversible, right? You हमारे पास दो reversible heat engine है, लेकिन दोनों के केस में source and sink same है, तो efficiency of reversible heat engine 1 will be equal to efficiency of reversible heat engine 2. मतलब आपके पास एक सोर्स है 100 डिग्री सेल्सियस पे, एक सिंक है 20 डिग्री सेल्सियस पे, हियर भी 20 है, हियर भी 100 है, राइट? हियर भी 100 है, यहाँ पे भी 20 है, राइट? अगर ऐसे केस है, दोनों अगर रिवर्सिबल बोला है तो दोनों का एफिशिएंसी सेम होगा, राइट? बिकॉज दोनों रिवर्सिबल है ना, और सोर्स एंड सिंक भी सेम है. ऐसा है तो योर एफिशिएंसी दोनों के केस में सेम होगा. सो आपके क्वेश्चन में ऐसे दे सकता है, दे कैन गिव यू this heat engine is a Carnot heat engine operating between 100 and 20. Second heat engine is a reversible heat engine operating between 100 and 20. Right? So when we say Carnot heat engine and when we say reversible heat engine, दोनों के लिए efficiency of both will be same. Clear? But that efficiency will be more compared to the irreversible heat engine efficiency. For example, we can see here Carnot heat engine efficiency is 80% for example. I'm taking it as 70% to be more realistic. Okay, 70%. So this also will have 70%. This will have what? 60%. Clear? So this is our first Carnot principle. Right? I hope you understood. Clear? So this is our first Carnot principle. Now we have a most important result for solving the problems, right? For solving gate questions, we have a most important result. That is, if you have a reversible heat engine or if you have any reversible cyclic device, right? When you have a reversible cyclic device, we are allowed to substitute QH by QL, or if it is QL by QH, for any reversible process, you are allowed to substitute it as TL by TH. For any reversible process, right, for any reversible cycle, right, for all reversible cycle, if it is a Carnot cycle also, right, QL by QH can be substituted as what? TL by TH. What is QL and QH? QL is the heat rejected, right, for heat engine. QH is the heat supplied. TL is what? Temperature. TH is temperature, right? TL is the temperature of sink. TH is the temperature of source. लेकिन ये substitution तभी होगा, right? This is valid only when TL and TH is substituted in Kelvin, right? You have to substitute TL and TH in Kelvin. Clear? Is it okay? Now we will see what is the equation for efficiency of heat engine. What is the equation for efficiency of heat engine? Tell me. Right? So efficiency of heat engine is 1 minus QL by QH. If you remember, how did you get 1 minus QL by QH? Your heat engine efficiency is what? Out of the QH, how much we are able to convert to work. This is your heat engine efficiency. So work output is what? QH minus QL divided by QH. So what will be this equation? 1 minus QL by QH. Clear? Now, if it is a Carnot heat engine or if it is a reversible heat engine, you can substitute the same equation as 1 minus TL by TH. You don't need the value of QL and QH if you have the temperature TL and TH. Simple. Problem is solved. Done. Now, what about refrigerator? What is the efficiency of a refrigerator? What is the equation for efficiency for a refrigerator? Out of the work input we will be writing it as QH minus QL. How much heat we are able to take from the fridge. Right? So how we used to write this equation, if you remember, it was 1 divided by QH by QL minus 1. So instead of QH by QL, you can substitute what? TH by TL. Simple. So instead of QH by QL, I am going to substitute TH by TL. Clear? So that is also done. Now what about the third one? Right? What about the third one? Clear? So that is heat pump. 1 minute. Clear? So the third one is your heat pump, right? What is the efficiency equation for a heat pump? What is the difference between refrigerator and heat pump in the equation? Heat pump, the objective is QH divided by QH minus QL. So your answer will be coming as 1 divided by 1 minus QL by QH. So in this equation, we can substitute, if it is a Carnot heat pump or a reversible heat pump, you can substitute what? 1 minus TL by TH. This is the efficiency of a Carnot heat pump. Simple. Clear? So I hope you can understand all the equations. Right? So understand it, right? Other than remembering these equations, you should be able to write the equation of, right? So for refrigerator, we won't be writing it as what? Efficiency. We will be writing it as COP of a refrigerator. For heat pump, we won't be writing it as this. We will be writing it as COP of heat pump. We have already discussed. There is no efficiency in refrigerator and heat pump. We will represent it by COP, right? So Carnot COP of a heat pump. Clear? So no need to remember these equations. At the time of exam, you should know how to write the equation of COP and efficiency of a heat engine. That's all, right? In that, you can substitute it by what? TL by TH. Lekin every time they will be giving the options in degree Celsius, right? That is, they will be giving you the temperature in degree Celsius. So you should be able to solve it in what? Kelvin. Clear? So we have some 3-4 gate questions are there that also we will solve. Then we will see. All are easy questions, okay? So that's why I told the toughest question in your Thermo 1 is from the closed system, right? Once that first law of thermodynamics is over, second law chapters are very simple. Clear? So if you remember this, all questions is easily solvable, right? Now we will see some questions. Clear? You can see the first question in gate. For a Carnot refrigerator operating between 40 and 25, the coefficient of performance is, right? You can see the options. 1, 1.67, 19.88, 39.74. So I hope you're able to see, right? The question is, you can see it is a question on Carnot refrigerator. For a Carnot refrigerator operating between 40, right, and 25, right? 40 and 25. So what is the equation for Carnot refrigerator? That is, this is for heat engine. Now this is for, clear? So in this TH by TL you can substitute and you can find the answer. Clear? Very simple, 40 and 25. But the problem is, right, the real problem is, if you substitute 40 and 25 here, your answer will be there in the option as well. But you cannot substitute 40 and 25. You have to convert it into Kelvin and then substitute. Clear? So then only you will be getting the answer. So those who have the calculator, do it. Clear? I hope you are able to see. So what will be TH? What will be TL? 1 divided by 40. So 40 plus 273. So 313 divided by 25 is 298 minus 1. You will get the answer. What is the answer? According to that, option C, right? 19.87. Right. So if you substitute without changing it into Kelvin, that option will also be there, right? So that you will be getting that answer, right? When you see the options, right, you will directly tick it, right? So the conversion is the only important thing you need to remember in this. Clear? So that is about what your Carnot refrigeration problem. In this is a question from gate 2008. You can see the next question. A heat engine. This is a question, I don't remember the year, but it is your Gate Academy booklet, you can see. So heat engine, 2.01 question. heat engine operates at 75% of the maximum possible efficiency. Right, heat engine is operating at 75% of the maximum possible efficiency. Ratio of heat source to the heat sink temperature is given 5/3. Right, heat source to heat sink temperature is given. Fraction of the heat supplied that is converted to work is, right, fraction of the heat supplied that is converted to work. That is a question, so you can see the option and solve it. Clear? So read the question carefully once again. So it is a question based on heat engine. So they have given, first thing what they have given us, heat engine operates at 75% of the maximum possible efficiency. The meaning is what? Actual efficiency, right, of the heat engine is, right, actual efficiency of the heat engine is 75% of maximum possible efficiency. What will be the maximum possible efficiency? It will be what? It will be, your efficiency is maximum when it is a Carnot heat engine. So 0.75% or 75% of efficiency of a Carnot heat engine. Right, so find the efficiency of a Carnot heat engine. What is the efficiency of a Carnot heat engine? You know, if it is a Carnot heat engine, efficiency is equal to, right, you know the equation, that is QH minus QL divided by QH. That is 1 minus QL by QH. If it is a Carnot heat engine, instead of QL by QH, you can substitute what? TL by TH. तो यहाँ पे क्या दिया है, right? You can see the question. The ratio of heat source to heat sink is 5/3. Heat source is the highest temperature. Heat sink is the lowest temperature. So TH by TL is given as 5/3. So what will be TL by TH? It will be 3/5. So 5 minus 3, 2. So your efficiency is 40%. 2/5. Right? Now, but the answer is not end there. Right? We don't have the answer there. Your answer is what? 75% of maximum possible efficiency. Because the question they are asking is what? What is the, they are not asking efficiency, is it? Yes, they are asking efficiency. Because you can see the question. The fraction of heat supplied that is converted to work. You can see the fraction of heat that is converted to work is your efficiency, na? Fraction of heat that is converted to work is your efficiency. Right? So they are asking the actual efficiency. What will be the actual efficiency? Actual efficiency will be 75% of 2/5. So find the answer. You will get the answer. So I think it is 30%, 0.3. Clear? So I hope all of you are getting. Right, it's very, very simple question. What is the fraction of heat that is converted to work? If you remember, like we have written this in the notebook, that is the fraction of heat that is supplied, fraction of heat supplied that is converted to work is called the thermal efficiency of a heat engine. Clear? So they are actually asking what? The thermal efficiency of a heat engine. Very clear. Right? So find it. You will get the answer. The answer will be 0.3, I guess. Right? So whichever option is there, you can solve it. Clear? So I hope you understood that as well. So this is the next question. The following heat engine produces power of 1 lakh kilowatt. Heat engine operates between 800 Kelvin and 300 Kelvin. It has thermal efficiency equal to 50% of that of Carnot engine for the same temperatures. Okay. The rate at which heat is absorbed from the hot reservoir is, right? So solve the problem. So read the question. Those who wanted to see this, just post the question, post the video and read the question. I will write the options on the board. Clear? So the question is what? The following heat engine, right? Following heat engine produces a power of 1 lakh kilowatt, right? So it produces a power of 1 lakh, that is work output is 1 lakh kilowatt. Clear? Output, right? Power. Now, the heat engine operates between 800 and 300. So what will be your TH? TH is 800 Kelvin. TL is 300 Kelvin. So it operates between what? These two temperature differences. Now the question is what? It has a thermal efficiency equal to 50% of the Carnot engine. So the efficiency is 50% of the Carnot engine efficiency. So what will be the efficiency of the Carnot engine? Right. So you can see the actual efficiency of this heat engine is equal to 0.5 multiplied by efficiency of Carnot heat engine. What is the equation for efficiency of Carnot heat engine? 1 minus, right, TL by TH is 3 by 8. So find it. So this will be what? This will be the efficiency of this heat engine. So what is the answer after solving this? You will be getting 0.3125, I guess. Right, you will be getting 0.3125. So this is the efficiency of your actual heat engine. Clear? Now they are asking what is the rate at which the heat is absorbed from the hot reservoir? That is, if you have a heat engine, right, they have given the work output, how much work output that they have already given. Now what is the rate at which heat is absorbed? So QH they are asking for the actual case, right? So what is the actual efficiency? 0.3125, which will be equal to what? Work output divided by QH. You have the work output, right? Then find the value of QH. Solve this, right? 1 lakh kilowatt divided by 0.3125. So you will be getting the answer. The final answer will be, what will be the answer? Let me check. After the calculation, you will get the answer 32,000, 32 and 4 zeros. Right? You will be getting 32. Your work output, or sorry, QH will be 32,000 kilowatt. I hope you are getting. Right? Solve this question. Clear? I hope this is also done, right? So solve this as well. Then I will give you one homework as well, right? So do it for tomorrow. The solution we will do in the next class. So solve this question for tomorrow's class. We will be solving this question tomorrow. So read the question. Consider two Carnot engines C1 and C2 shown in the figure. Reservoir R1, C1, reservoir R2, C2, R3. Right, efficiencies of these engines C1 and C2 are given 0.40, 0.35 respectively. If the temperature of reservoir R1 is 800, then the temperature of reservoir R3 is. Clear? So solve this and come for tomorrow. Then we will be discussing this question. Clear? Solve this particular question and we'll see in the next class. Right, so that we will be solving in next class. So that is the end of your almost second law is over. Right, that is questions based on refrigerator, heat pump and your heat engine is over. Now from tomorrow mostly you can solve the remaining problems, then we will start our last topic in Thermo 1, that is your entropy, right? So once that entropy part is also over, we can start our Thermo 2. Clear? So that's all, right? So we will be meeting for tomorrow's class. Thank you very much.